Hello, everyone. I'm Moony. Today, I'm very glad to take the conference of Code Blue. And today, I will introduce the topic of how we fast and exploit the Apple call, the passive framework and the context enlightenment framework into the Apple call and exploit. We have exploited the vulnerabilities and root the Mac OS operating system of EI Captain version. Okay. This is my agenda. First, I will introduce a little about me and my partner. And second, I will introduce our passive fuzzing framework about how we design the approach and consideration, and how we implement the passive fuzzing framework in detail. And also, we will introduce the best practice or tips during our fuzzing activities. And in the last part, I will introduce the tips and the best practice, how we exploit the vulnerabilities we have found using the passive fuzzing framework, and how we root it in OS X machine. Okay, this is me. I have worked about 7 years about security, developing sandbox system, and also I'm focusing on Mac, Windows, and Android kernel vulnerabilities. And this is my partner, Jack. He has worked about 10 years in security, mainly focused on browser and document vulnerabilities, and also Mac Windows kernel, and also virtualization vulnerabilities. But Jack has broken his leg so badly, so he could not travel with me. So just best wishes to Jack. So why we are here? Because of this. Here are the CVE lists, which we have been credits using our passive fuzzing framework. About the CVEs are from the Apple vendor, and some are from the CDI, just like this. Okay, actually we have used several of the vulnerabilities to root OS X version 10.11.3 version using these vulnerabilities. In this part, I will introduce how we design and how we consider our approach to implement our passive fuzzing framework. Okay, before the first, let's see how other researchers do fuzzing towards macOS kernel. The traditional way is that the researchers would open the services which are exposed by our kit and pour the fast data to the important API, such as ESL Connect method and so forth. And the fast data will transfer it to the kernel. And if the kernel could not handle the fast data correctly, then the whole kernel would crash. This is the active way to fast OS X kernel, as we call it. However, there exists several condition dependency, as we have seen. For example, we have category the condition dependency into 3 categories: the call sequence dependency, and the input dependency, and the timing dependency. For example, for the call sequence dependency, the researcher must open the device. For example, our camera I/O service first, and power on the service. Then you can do your active fuzzing in a normal way. And if any of the initialization failed, then the fuzzing activity would fail in the early age. And also there exists the input data dependency. Take the Apple HDA engine, for example. There exists one parameter which must be allocated from the user mode, and this buffer is transferred as a pointer to the kernel mode. So if this buffer is not correctly allocated from the user mode, then any call to this service would fail. Another is the timing dependency. As we have found, there exists some services that timely appear. For example, if you open one DMG file, then this service, LHDIX devices out kernel service would appear in your OS X machine. And another traditional way to hunt vulnerabilities of OS X is code revealing. So this kind of code revealing would cost much effort because there exists so many binaries, which is closed sourced, and the researcher must reverse engineer the binary and select so many interfaces and so many services among the binaries. So this kind of code revealing is not scalable, and it will cost much effort and much time for the researcher. So what is our approach? The key point of our approach is why not play? Why don't we play games for bugs? Small games, for example, heavy online games you play, and the small bounty of bug hunting you have got. Is it possible? Okay. The normal scenario for our fuzzing is just like this. Then this is a real OS X machine, and I have plotted our passive fuzzing framework on the real machine here. And then we will launch any online games, for example, this one. And suddenly it will crash like this. You can see the code stack log on the screen here. So we can get the kernel dump of the OS X machine, and we can reproduce the kernel crash and get bounty from the CDR if you want. Okay, so how do we think of it? We can compare this passive fuzzing framework with dam poison. You can imagine that in a river, the water in the upstream will run down to the river dam, and the river dam will intercept all the water from the upstream. And if we poison the dam, and the water will be poisoned, the pointed data will run down to the downstream of the river. Then all the fish in the downstream will die. Okay. So in our passive fuzzing, the downstream data is lack of the user mode data. The user mode data and the user mode exception will all intercepted by hooking all important APIs, such as ETL connect method and so forth. And the fast data by our hooker or by our passive fuzzing framework will be fast and delivered to the kernel mode user. The kernel mode user data is then delivered to the target driver. If the driver could not handle the fast data correctly, then the whole kernel would crash. Just like that, all the fish in the downstream will die. And the reproduction process is just similar. When we reproduce the kernel crash, it's just like that. We will track the origin of the poison in the river dam. Okay, and then I will introduce the implementation in detail for you. First of all, let's take a glance of our normal routine. This is the real picture of our fuzzing. In the left one, we call it a server machine, and the right one, we call it a client machine. We use the sandbox connection to debug the server machine using our client machine if the server machine crashes. And first, we will plant our passive framework on the server machine here. And then we would launch any applications if we want. And suddenly, because of our fuzzing activities, the server machine would crash just like this. It will show many code stacks log on screen. And then it will generate a call stack, call dump in the server. And we could debug the server machine using a network or using a sandbox as you like. And the generated call stack is transferred to the client machine. So the client machine could get all the info which could reproduce the kernel crash easily. Okay, that's this overview architecture. This one is this one from this point is a kernel layer, and the upper one is the use mode layer. And we put our passive fuzzing framework on the kernel layer here. And the whole process would be like this. If the target application, for example, one online game is executed on your machine, then all the data and all important APIs are hooked in kernel mode as part of our passive fuzzing framework here, hooker. And this is the API list we will hook in our kernel mode. And the intercepted data and the intercepted API are transferred first to our condition checker module. If the data and the APIs are interesting for our researcher, then it could be sent out through contact matter to alert the researcher about which module is buggy or which interface is so vulnerable and so that. Then else, the temporal module would fuzz the data from the use mode and transfer it to the original function here. Then the original function would transfer the data to the target devices. For example, the sandbox, USB, HDA, and so forth, if you like. And probably the fast data will cause the whole kernel to crash. So this is the pseudocode for our passive fuzzing framework. In the target application here, we would handle the parameters transferred from the use mode. And we will first whitelisting the parameter and check the call stack info of the parameter, and also check whether the parameter is in the blacklist. If the data should be fast as we design, then we should record the parameters in our design and send them out. For example, through network or through NVRAM, non-variable memory, and so forth. And then we will fuzz the data. The fuzz data will deliver to the original API. Then the original API would call the target devices. Probably, if you're calling the original API with the fuzz data, the kernel would crash, as we oppose. Okay, more detail about our hooker module and temporal module. Actually, we have designed our hooker module by inline hook in kernel mode, because in this way, you can intercept all the important APIs from all user processes, just one-to-many design. Another design is about temporal. Actually, the principle with fast data is that we should only fuzz the data content which could be controllable or accessible directly from the user mode. And we do not care about the data which is inaccessible or uncontrollable by the user. So take the ISL connect call method, for example, we would care about these three buffer contents, and we do not care about the size field of the parameter, because the system OS X itself would check the validity of the size parameter. Okay, let's take a real example. Here is the real kernel crash call stack, which we have found and which we have not reported to the vendor. And you can see that upper one is the bottom of the stack, and the lower one is the upper one is top of the bottom, and the lower one is the bottom of the core stack. And we have set the trampoline function here. Trampoline is our connect core method, and it will inline hook is our connect core method, which is the system API. And this API will pass, for example, connection of user client or user service, selector function number for the service is an integer, and also scalar input, inbound input, OR input, and so forth. And also there would be output related information. Actually, so also hooker we have set is layered from smaller scope to bigger scope. For example, these two API is our connect core method is our async method. It's related to our kit module, which is related to driver interface. And these two quit mapping in task, allocate use client trap is related to OSX kernel itself. And these two, IPC, message send and get, is related to match inter-process communication mechanism of OSX. And also copy-IO is general in the whole kernel. Okay, like take a glance of all the hook in our source code. Actually, we have set all the hook by flag using Boolean. And if you can activate the hooker by set the Boolean from false to true. It could take effect. It would take effect. So another point is about condition checker. So why do we introduce condition checker? Mainly, the basic reason for the condition checker is to bypass all the noise because of our passive fuzzing. For example, when during our passive fuzzing framework, it could interfere with all the normal activities when you're using your OSX machine. For example, it would cause black screen, but the kernel is active. It would cause harm of your kernel, but it also do not crash. And also, we will bypass the crashes we have reproduced error. Another point is about hunting vulnerability. So we can find some specific type of vulnerability using condition checker. This part I will talk it later. And how does the checker works? Actually, we have designed the condition checker in different dimensions, and we have introduced some basic syntax using our condition checker. For example, and, or, wild match, whitelisting, blacklisting, and so forth. And also, the condition checker will cover different property of system API, which is our target. For example, the process, the module function, and also the data, the core stack, and the miscellaneous. About the process, we could care about, for example, the user ID. We can distinguish whether current process is root or not. And we can care about the process name. For example, Safari, we can distinguish whether current process could be remotely controlled or whether current process is sandbox evasion. And also, we would care about module name and function names. Symbol name means function name and function address. This part is about the offset of the target function from the beginning of the function to the end of the function. Take an example. In this whitelisting detail control, we would care about proc name, user ID, driver name, driver bundle name, driver class name, and selector of the function, and so forth. For example, in this one, It means it is the Windows Server process, and we will bypass the ACTL surface classes, and we will bypass this selector, because if you call this selector, you can cause the kernel crash. We have reproduced the crash. This is our index of crash. And also, we will care about data and the call stack. About data, we will care about whether the address is readable, writable, or executable, and whether the data is read from the user or just read from kernel to user, and whether the data address is in user mode or kernel mode. About the call stack, we will care about the information of the frame of any frame of the call stack. For example, we will care about the return address in the call frame, and the stack level from the top from bottom to the top in the call stack. Take example. This is the call stack. We will care about routine name, routine address, and the stack level layer. For example, if the return address is among this function, and if this function is in this function is in layer of this part in the whole call stack, then we will care about it. There are also some miscellaneous condition checkers in our design. For example, use client. Use client is specific to allocate fuzzing. For example, about the use client related fuzzing, we would care about, for example, program name, driver name, function selector. For example, this is the class name of the ADPM use client, ADPM client, and this is the function number we're caring about. And this is match message inter-process communication part related condition checker. In this condition checker, we would care about, for example, match message ID, match message ID from, match message ID to. Actually, all the match ID could be divided into different parts, and we summarize them here. For example, if the message is among this range, it means that the message is about allocate subsystem, and if they are in this range, it means it is the MacPort subsystem range. So we can distinguish all the different parts of our fuzzing target. Another point is about context, as I have mentioned before. So what is context, and why do we introduce context? Actually, the context means the pattern accumulated during our fuzzing activities. So it could give much enlightenment to the researcher for code revealing. For example, it could lead to tell the researcher which module is more buggy than the other module, and which interfaces or which APIs are more important or more vulnerable than the other APIs. So this is the context is not vulnerability itself, but it could indicate suspicious vulnerabilities. And actually, we have implemented the context mechanism in our condition checker. Take two examples. About the context, there are basically two kinds of context. The first one is to indicate the memory corruption related context. Take a real example. If we have found in the kernel mode that an API call to the create mapping in task is called, and one of its parameter is used as a buffer size, then we could define this sequence of API calls or the scenario as typical over-buffer flow vulnerability. And if we found, for example, from the output buffer of ESL connect method, one of its parameter contains the prefix of 0xFFF, then it would indicating that the kernel mode use buffer address is leaked from kernel mode to user mode. So by this kind of indication, we could get different kind of kernel vulnerabilities. Okay, so far during our passive activity, what best practice or what tips have we gotten? Then in this part, I will introduce some of best practice and tips. It's about fuzzing source, fuzzing stability, reproduction, automation, and a bit missing challenge. About the fuzzing process, about the fuzzing source, we recommend you to download and launch different kinds of applications from for example, Apple Store, because different applications towards different hardware devices could generate different data and exception to the system or to our passive fuzzing framework. Then you would have a high probability to get vulnerability. For example, you could download and run, for example, online games, FaceTime, USB divided, USB related Bluetooth, Wi-Fi, or VMware, virtual machine, DirectX related application from the Apple Store. And also you could download different suspicious applications from different channels here. And we have found that using the passive fuzzing framework, some module is more vulnerable and more crashable than the other module. For example, the graphic related module. Then the other kind of module could not be touched by our fuzzing. So you can complement the passive fuzzing by active fuzzing, just like this. Another point is about fuzzing stability. In our passive fuzzing, it will interference the normal use of your OS X machine. So you should bypass the noise or interference using our condition checker. Another part is about reproduction. Actually, we have recorded all the parameters before we fuzz data. And also, we will send out the whole call stack, the whole kernel call dump if the crash happened from the server machine to the client machine. This is some real tips for you. For example, you could set up your dump server just like this, and you could using the sendbot wire to connect your server and client machine here. To make all the passive fuzzing framework automation, we recommend you can put your fuzzing framework into a guest OS machine. For example, you can put them in VMware Fusion and QEMU and so like that. And you can create one initialized snapshot. And then you could run your passive working from this snapshot. And if the guest OS crashes, you can get the whole kernel dump for your reproduction. And then you can restore the initiable snapshot. Some miscellaneous tricks. Actually, maybe you could, for example, open some specific devices and initialize the devices into the normal state, and then suddenly you can plant your passive fuzzing framework, and then the more probability you will get is the kernel crash. Okay, the last part we will introduce how we exploit the OS X machine with the vulnerabilities we have found. First of all, I will introduce some security mitigation, which is introduced by OS X latest version, SIP, kernel address layout randomization, supervisor mode access prevention, and supervisor mode execution prevention. These features are implemented in the 20 and 22 bits of CR4 register here. Actually, we can ignore SIP because this is irrelevant to OS X kernel root. We would care about KLSR as SMAP, SMEP. To bypass SM, actually we have no vulnerability to bypass the kernel address randomization. We just use the old vulnerability here. It could leak the key slice of the text segment in the kernel mode to user mode. And we have found the vulnerability of this in this image. It could leak the kernel heap address from the kernel mode to user mode. Using this vulnerability, we could bypass SMAP, access prevention. And also we could get an any call execution here, vulnerability in this image module. Using this vulnerability, we could control the EIP or RIP register. And we could lead the execution to the RP chain. In this RP chain, we will disable the CR4 register to shut down SMAP and SMEP. Then the payload in the user mode could be executed in the kernel directly. And also, the exploit process is related to heap spray. There are some tips during heap spray. Actually, there is some traditional way to use OS unserialized API to allocation and occupy kernel buffer in kernel mode. This way is introduced by Stephen Isser in 2012. Actually, this API would handle an XML likable input buffer. The key and the value. The value is the array, and the array is composed of several data. It's the OS data. So this data could be allocated in the kernel mode, and the format of the kernel mode data is exactly predictable. However, using this API, using this API directly would fail to heap spray because usually there followed an OS object release to the buffer you have ever allocated. So in most cases, if you call the wrapper API of OS unserialized, it would then allocate the buffer first and then release it. So there is no effect. So we must find a wrapper API which would just allocate kernel buffer in kernel mode, but it would not freeze the buffer in this cycle of API call. We have found the API call about the IO registry component of OS X. Actually, IO registry component is similar to device manager in Windows. And always we have a cache, and we have found the cache. So we have found this kind of the wrapper, secure sleep system options, which is the service of IOMP root domain about select 7. And if you call it, in the use mode just like this. Then it would allocate the kernel buffer in the kernel mode. That is the exploit process in the overview. At the first step, here, we could use the vulnerability to bypass KLSR to get the kernel text address and build up our payload using these APIs like this. And then we would use our this is vulnerability 1, and then we would use the vulnerability we have found. This is vulnerability 2. It would leak the kernel buffer here, L command. It will leak the address in the kernel mode to the use mode. And then we would occupy we would release freeze L command buffer here. And then we would keep spray the L command with our new OS data. The OS data contains specially defined RP chain and specially defined stack pervert like this. And finally, we will use our third vulnerability to execute the leak address plus 0650 offset. Then it would call to the stack pervert. The stack pervert would change the stack here, RP chain. RP chain would then first disable the 20 and 21 bits of CR4 register. So to close SMAP and SMEP. And finally, we could call the payload in the user mode directly. Okay, let's see the whole process from a different view. First, we will build up our payload in the user mode, which will use the leaked address of the KLSR. And then we would normally allocate an IO command buffer in the kernel mode. And we use vulnerability 2 to leak the heap address of this object. And then we will free the IO command buffer and occupy it using OS data. The OS data contains such data which are specially designed like this: stack pervert, RP chain, and the payload. And then we use the third vulnerability, which is any call execution vulnerability. Then it would call to leak address plus offset, which would trigger stack pervert. Stack pervert would change the stack to our RP chain buffer, and the RP chain buffer would then disable SMAP, SMEP using RP get it. And then it would finally call payload, which is layered in the user mode. Okay, let's see the demo video. First, we could see that we are not root. ID command, we could see that the user ID is not 0. And then we could open any DMD file so that the IOHDIX service could appear in your OS X machine. And then we use our we launch up our exploit application. In this application, it would use 3 vulnerabilities. Take a moment. And finally, we could see that we are root. We could see the ID is 0. Okay, thank you. This is my last page of my PPT.